Chapter 11, Work and Energy. In the previous few chapters, we have talked about ways of describing the motion of objects, the cause of motion and gravitation. Another concept that helps us understand and interpret many natural phenomena is work. Closely related to work are energy and power. In this chapter, we shall study these concepts. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strenuous require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, or find a safe place to live. Also, we engage some animals to lift weight, carry loads, pull carts, or plow fields. All such activities require energy. Think of machines. List the machines that you have come across. What do they need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machines need energy? 11.1 Work. What is work? There is a difference in the way we use the term work in day-to-day life and the way we use it in science. To make this point clear, let us consider a few examples. 11.1.1 Not much work in spite of working hard. Kamali is preparing for examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thought, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She spends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. You are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You get completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You have exerted yourself and have spent quite a bit of your energy. Have spent quite a bit of your energy. Are you doing work on the load? The way we understand the term work in science, work is not done. You climb up the steps of a staircase and reach the second floor of a building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work. In day-to-day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand this, let us do the following activities. Activity 11.1 Do this. We have discussed in the above paragraphs a number of activities which we normally consider to be work. In day-to-day life, for each of these activities, ask the following questions and answer them. 1. What is the work being done on? 2. What is happening to the object? 3. Who? What is doing the work? 11.1.2 Scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. 1. A force should act on an object, and 2. The object must be displayed. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. A block is pulling a cart. The cart moves. There is a force on the cart and the cart has moved. Do you think that work is done in this situation? Activity 11.2. Do this. Think of some situations from your daily life involving work. List them. Discuss with your friends whether work is being done in each situation. Try to reason out your response. If work is done, which is the force acting on the object? What is the object on which the work is done? What happens to the object on which work is done? Activity 11.3. Do this. Think of situations when the object is not displayed in spite of a force acting on it. Also think of situations when an object gets displacement in the absence of a force acting on it. List all the situations that you can think of for each. Discuss with your friends whether work is done in these situations. 11.1.3 Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance S in the direction of the force figure. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done equal to force into displacement. W equal to Fs. Fs figure. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. In equation, if F equal to 1 Newton and S equal to 1 meter, then the work done by the force will be 1 Newton meter. Here the unit of work is Newton meter, Nm, or joule, J. Thus 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Look at equation carefully. What is the work done when the force on the object is 0? What would be the work done when the displacement of the object is 0? Refer to the conditions that are to be satisfied to say that work is done. Example 11.1. A force of 5 Newton is acting on an object. The object is displaced through 2 meter in the direction of the force. Figure. If the force acts on the object all through the displacement, then work done is 5 Newton into 2 meter equal to 10 Newton meter or 10 joule. 5 Newton, 2 meter. Figure. Question 1. Comment this. 8 meter, 7 Newton. Figure. Consider another situation in which the force and the displacement are in the same direction. A baby pulling a toy car parallel to the ground as shown in figure. The baby has exerted a force in the direction of displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Figure. Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 degrees. Let the object stop after a displacement S. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is F into minus S or minus F into S. It is clear from the above discussions that the work done by a force can be either positive or negative. To understand this, let us do the following activity. Activity 11.4. Do this. Lift an object up. Work is done by the force exerted by you on the object. The object moves upward. The force you exerted is in the direction of displacement. However, there is the force of gravity acting on the object. Which one of these forces is doing positive work? Which one is doing negative work? Give reasons. Work done is negative when the force acts opposite to the direction of displacement. Work done is positive when the force is in the direction of displacement. Example 11.2. A porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. Solution. Mass of luggage m equal to 15 kg and displacement s equal to 1.5 meter. Work done w equal to f into s equal to mg into s equal to 15 kg into 10 meter second 2 inverse into 1.5 meter equal to 2 to 5 kg meter second 2 inverse meter equal to 2 to 5 Newton meter equal to 2 to 5 joule. Work done is 2 to 5 joule. Questions 1, 2, 3, 4. Comment this. 11.2. Energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural sources of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth and the tides. Can you think of other sources of energy? Activity 11.5. Do this. A few sources of energy are listed above. There are many other sources of energy. List them. Discuss in small groups of how certain sources of energy are due to the sun. Are there sources of energy which are not due to the sun? The word energy is very often used in our daily life, but in science, we give it a definite and precise meaning. Let us consider the following examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. You must have seen that when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We have also observed children winding a toy, such as a toy car, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the objects occur through different means. the capable of doing work. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of work, that is joule, J. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule, kg, kj in used. 1 kj equals 1000 joule. 11.2.1 Forms of energy. Luckily, the world we live in provides energy in many different forms. The various forms include mechanical energy, potential energy plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Think it over. How do you know that some entity is a form of energy? Discuss with your friends and teachers. James Prescott Joule, 1818 to 1889. James Prescott Joule was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work called joule is named after him. 11.2.2 Kinetic energy. Activity 11.6. Do this. Take a heavy ball, drop it on a thick bed of sand. A wet bed of sand would be better. Drop the ball on the sand bed from height of about 25 cm. The ball creates a depression. Repeat this activity from heights of 50 cm, 1 meter and 1.5 meter. Ensure that all the depressions are distinctly visible. Mark the depressions to indicate the height from which the ball was dropped. Compare their depth. Which one of them is deepest? Which one is shallowest? Why? What has caused the ball to make a deeper dent? Discuss and analyze. Activity 11.7 Do this. Set up the apparatus as shown in figure. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. Place a known mass on the pan so that the trolley starts moving. Figure F. The trolley moves forward and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displayed. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. From where does this energy come? Repeat this activity by increasing the mass on the pan, in which case is the displacement more. In which case is the work done more? In this activity, the moving trolley does work and hence it possesses energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. How does a bullet pierce the target? How does the wind move the blade of a windmill? Objects in motion possesses energy. We call this energy kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possesses kinetic energy. In short, Kinetic energy is the energy processed by an object due to its motion. The kinetic energy of an object increases with its speed. How much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displayed through a distance s when a constant force F acts on it in the direction of its displacement. From equation, the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. In section, we studied three equations of motion: the relation connecting the initial velocity u and final velocity v of an object moving with a uniform acceleration a, and the displacement s is v square minus u square equal to 2as. This gives s equal to v square minus u square by 2a. From section, we know F equal to ma. Thus, using in equation, we can write the work done by the force F as W equal to ma into v square minus u square by 2a, or W equal to half m v square minus u square. If the object is starting from its stationary position, that is u equal to 0, then W equal to half m v square. It is clear that the work done is equal to the change in the kinetic energy of an object. If u equal to 0, the work done will be half mv square. Thus, the kinetic energy processed by an object of mass m and moving with a uniform velocity v is Ek equal to half mv square 11.5. Example 11.3. An object of mass 15 kg is moving with a uniform velocity of 4 meters second inverse. With what is the kinetic energy processed by the object? The solution: mass of the object m equal to 15 kg, velocity of the object v equal to 4 m s inverse. From equation, Ek equal to half mv square equal to half into 15 kg into 4 meters second inverse into 4 meters second inverse equal to 120 joule. The kinetic energy of the object is 120 joule. Example 11.4. What is the work to be done to increase the velocity of a car from 30 km per hour to 60 km per hour if the mass of the car is 1500 kg? Solution: mass of the car m equal to 1500 kg, initial velocity of car u equal to 30 km per hour equal to 30 into 1000 meter by 60 into 60 s equal to 25 by 3 meter per second. Similarly, the final velocity of the car v equal to 60 km per hour equal to 50 by 3 meter per second. Therefore, the initial kinetic energy of the car Eki equal to half mu square equal to half into 1500 kg into 25 by 3 meter per second whole square equal to 156,250 by 3 joule. The final kinetic energy of the car Ekf equal to half 1500 kg into 50 by 3 meter per second whole square equal to 625,000 by 3 joule. Thus, the work done equal to change in kinetic energy equal to Ekf minus Eki equal to 156,250 joule. Questions 1, 2, 3. Comment this. 11.2.3 Potential energy activity. 11.8 Do this. Take a rubber band, hold it at one end and pull from the other. The band stretches. Release the band at one of the ends. What happens? the band will tend to regain its original length. Obviously, the band had acquired energy in its stretched position. How did it acquire energy when stretched? Activity 11.9. Do this. Take a slinky as shown below. Ask a friend to hold one of its end. You hold the other end and move away from your friend. Now you release the slinky. What happened? How did the slinky acquire energy when stretched? Would the slinky acquire energy when it is compressed? Activity 11.10. Take a toy car, wind it using its key, press the car on the ground. Did it move? From where did it acquire energy? Does the energy acquired depend on the number of windings? How can you test this? Activity 11.1. Activity 11.11. Lift an object through a certain height. The object can now do work. It begins to fall when released. This implies that it has acquired some energy. It raised to a greater height. It can do more work and hence possesses more energy. From where did it get the energy? Think and discuss. In the above situations, the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. You transfer energy when you stretch a rubber band. The energy transferred to the band is its potential energy. You do work while winding the key of a toy car. The energy transferred to the spring inside the stored as potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration. Activity 11.12. Take a bamboo stick and make a bow as shown in figure. Place an arrow made of a light stick on it with one end supported by the stretched string. Now stretch the string and release the arrow. Notice the arrow flying off the bow. Notice the change in the shape of the bow. The potential energy stored in the bow due to the change of shape is thus used in the form of kinetic energy in throwing of the arrow. Figure an arrow and the stretched string on the bow. 11.2.4 Potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Figure H. Ground. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object mg. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, work done W equal to force into displacement mg equal to h. mg into h equal to mgh. Since work done on the object is equal to mgh and energy equal to mgh units is gained by the object, this is the potential energy EP of the object, EP equal to mgh. More to know. The potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and final position of the object and not on the path along which the object is moved. Figure. Shows a case where a block is raised from position A to B by taking two different paths. Let the height AB equal to h. In both the situations, the work done on the object is mgh. Figure A to B h path 1, A to B path 2. Example 11.5. Find the energy processed by an object of mass 10 kg when it is at a height of 6 meter above the ground, given g equal to 9.8 meter per second square. Solution. Mass of the object m equal to 10 kg, displacement height h equal to 6 meter, and acceleration due to gravity g equal to 9.8 meter per second square. From equation, potential energy equal to mgh equal to 10 kg into 9.8 meter per second square into 6 meter equal to 588 joule. The potential energy is 588 joule. Example 11.6. An object of mass 12 kg is at a certain height above the ground. If the potential energy of the object is 480 joule, find the height at which the object is with respect to the ground, given g equal to 10 meter per second square. Solution. Mass of the object m equal to 12 kg, potential energy EP equal to 480 joule, EP equal to mgh. 480 joule equal to 12 kg into 10 meter per second square into h. H equal to 480 joule by 120 kg meter per second square equal to 4 meter. The object is at the height of 4 meter. 11.2.5. Are various energy forms interconvertible? Can we convert energy from one form to another? We find the natural number of instances of conversion of energy from one form to another. Activity 11.13. Do this. Sit in small group, discuss the various ways of energy conversion in nature. Discuss following questions in your group. A. How do green plants produce food? B. Where do they get their energy from? C. Why does the air move from place to place? D. How are fuels such as coal and petroleum formed? E. What kinds of energy conversions sustain the water cycle? Activity 11.14. Do this. Many of the human activities and the gadgets we use involves conversion of energy from one form to another. Make a list of such activities and gadgets. Identify in each activity gadget the kind of energy conversion that takes place. (11.2.6) Law of conservation of energy in activities, and we learned that the form of energy can be changed from one form to another. What happens to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created or destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be half mv square. As the fall of the object continues, the potential energy would decreases while the kinetic energy would increase. When the object is about to reach the ground, h equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy equal to constant, or mgh plus half mv square equal to constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. Here the effect of air resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into kinetic energy. Activity 11.15. Do this. An object of mass 20 kg is dropped from a height of 4 meter. Fill in the blanks in the following table by computing the potential energy and kinetic energy in each case. Height at which object is located m. Potential energy EP equal to mgh j. Kinetic energy ek is equal to mv square by half j. EP plus ek j. 4, 3, 2, 1, just above the ground. Comment this. For simplifying the calculations, take the values of g as 10 meter per second square. Think it over. What would have happened if nature had not allowed the transformation of energy? There is a view that life could not have been possible without transformation of energy. Do you agree with this? (11.3) Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy do work at different rates. Let us understand this from the following activity. Activity 11.16. Consider two children, say A and B. Let us say they weigh the same. Both start climbing up a rope separately. Both reach a height of 8 meters. Let us say it takes 15 seconds while B takes 20 seconds to accomplish the task. What is the work done by each? The work done is the same. However, A has taken less time than B to do the work. Who has done more work in a given time, say in 1 second? A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. We talk of the power of machines like motorbikes and motor cars. The speed with which these vehicles change energy or do work is the basis for their classification. Power measures the speed of work done. That is, how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power is given by power equal to work by time, or P equal to W by T. The unit of power is watt in honor of James Watt, 1736-1819, having the symbol W. 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joule per second. 1 watt equal to 1 joule per second, or 1 watt equal to 1 joule second inverse. We express larger rates of energy transfer in kilowatts kW. 1 kilowatts equal to 1000 watts. 1 kilowatts 1000 watts. 1 kilowatt 1000 joule per second. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Example 11.7. Two girls, each of weight 400 Newton, climb up a rope through a height of 8 meter. We name one of the girls A and the other B. Girl A takes 20 seconds while B takes 50 seconds to accomplish this task. What is the power expended by each girl? Solution 1. Power expended by girl A. Weight of the girl mg equal to 400 Newton. Displacement height h equal to 8 meter. Time taken t equal to 20 seconds. From equation, power P equal to work done by time taken equal to mgh by t equal to 400 Newton into 8 meter by 20 second equal to 160 W watt. 2. Power expended by girl P. Weight of the girl mg equal to 400 Newton. Displacement height h equal to 8 meter. Time taken t equal to 50 seconds. Power P equal to mgh by t equal to 400 Newton into 8 meter by 50 second equal to 64 W or watt. Power expended by girl A is 160 watt. Power expended by girl B is 64 watt. Examples 11.8. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 cm, find his power. Take g equal to 10 meter per second square. Solution. Weight of the boy mg equal to 50 kg into 10 meter per second square equal to 500 Newton. Height of the staircase h equal to 45 into 15 by 100 meter equal to 6.75 meter. Time taken to climb t equal to 9 seconds. From equation, power P equal to work done by time taken equal to mgh by t equal to 500 Newton into 6.75 meter by 9 seconds equal to 375 W. Power is 375 watt. Questions 1, 2, 3, 4. Comment this. 11.3.1. Commercial unit of energy. The unit joule is too small and hence is inconvenient to express large quantities of energy. We use a bigger unit of energy called kilowatt hour, kWh. What is 1 kilowatt hour? Let us say we have a machine that uses 1000 joule of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kilowatt hour, 1 kilowatt hour of energy. Thus, 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second or 1 kilowatt. 1 kilowatt hour equal to 1 kilowatt into 1 hour equal to 1000 watt into 3600 second equal to 360000 joule. 1 kilowatt hour equal to 3.6 into 10 to the power 6 joule. The energy used in households, industries and commercial establishments are usually expressed in kilowatt hour. For example, electrical energy used during a month is expressed in terms of units. Here, 1 unit means 1 kilowatt hour. Example 11.9. An electric bulb of 60 watt is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. Solution. Power of electric bulb equal to 60 watt equal to 0.06 kilowatt. Time used t equal to 6 hour. Energy equal to power into time taken equal to 0.06 kilowatt into 6 hour equal to 0.36 kilowatt hour equal to 0.36 units. The energy consumed by the bulb is 0.36 units. Activity 11.17. Do this. Take a close look at the electric meter installed in your house. Observe its feature closely. Take the readings of the meter each day at 6:30 am and 6:30 pm. Do this activity for about a week. How many units are consumed during a daytime? How many units are used during night? Tabulate your observation, draw inference from the data, compare your observation with the details given in the monthly electricity bill. One can also estimate the electricity to be consumed by specific appliance by tabulating their known wattage and hours of operation. What you have learned. Work done on an object is defined as the magnitude of the force multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule equal to 1 Newton into 1 meter. Work done on an object by a force would be zero if the object is zero. An object having capability to do work is said to possess energy. Energy has the same unit as that of work. An object in motion possesses what is known as the kinetic energy of the object. An object of mass m moving with velocity v has a kinetic energy of half mv square. The energy possessed by a body due to its change in position or shape is called the potential energy. The gravitational potential energy of an object of mass m raised through a height h from the Earth's surface is given by mgh. According to the law of conservation of energy, energy can only be transformed from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation always remains constant. Energy exists in nature in several forms such as kinetic energy, potential energy, heat energy, chemical energy, etc. The sum of kinetic and potential energies of an object is called its mechanical energy. Power is defined as the rate of doing work. The SI unit of power is watt. 1 watt equal to 1 joule per second. The energy used in 1 hour at the rate of 1 kilowatt is called 1 kilowatt hour. Exercises. Do this and comment this.